Hi everyone, welcome to this machine learning and MFG game seminar. Today we are very happy to have Panayotis Mertikopoulos. So thank you very much for accepting the invitation and managing to make it for this seminar. And so Panayotis is going to talk about learning in non-atomic games. Thanks a lot, and the floor is yours.
Yes, thank you. Thank you very much for inviting me. It's a real pleasure to be here and present. And as I was saying right before, I have to present my apologies in the sense that this is not going to be strictly about Minfield games. Actually, uh, I'm going to present some results that we have for learning in non-atomic games, which is sort of the basis that we are trying to work up on in order to reach to similar results in Minfield games, where of course things are considerably more difficult. So at least we're trying to establish a baseline of what we can expect in terms of results. And the last thing I want to say before I begin is that I mean, relatively few of us. Please stop me at any point. I'd much rather, have a very interactive talk, insisting upon one point rather than just powering through the slides and losing you at some point. So yeah, to begin, I should say that the motivation actually for this project, for this series of results that I'm going to present, actually goes a bit back, a bit even before starting being interested in Minfield games, and when we're the point of departure was actually traffic in cities, where, I mean, Mathieu, you're in New York. You have seen the beautiful morning commutes there, and the idea, what we're trying to do is to, well, first of all, to model it as a game, and second, from by studying the equilibria of this game, to try to find algorithms, adaptive algorithms that the users might employ, or by following the recommendation of an app like Google Maps, to try and reach sort of an equilibrium where at least every individual commuter is happy. At least he's not more frustrated with their choice than they would have been by taking another route. All right. So this the basic thing that we want to see here is what would an online learning process look like in this type of games? And so in particular, what we have in mind, the general framework that we have in mind, is that, for every epoch in time and every individual player or commuter in this very large non-atomic play field, which is New York, well, the player chooses an action, which could be, for instance, the route to go from, I don't know, the Apollo Theater to Harlem. They receive their reward or incur a certain loss, which is the time that they spend commuting in New York. And then they may get some feedback, some continuous feedback, for instance, through an app that they might be using, or by comparing experiences with other commuters when they reach their destination. And through that feedback and their individual experiences, they might update their choices the next time around, play again, and essentially what we would like to see is whether this process, this online decision process, this non-atomic online learning process, actually converges to some sort of a stable state or whatnot. All right, so there are several elements here at play. There is time, whether it is continuous or discrete. There is the set of players, whether we're talking about a continuous, non-atomic population of players, or a finite number of players. Their actions, whether they're continuous or finite. Also, the reward mechanism, whether everything is determined by a game or if there are some outside influences. So, for instance, like the weather, from the nature, from the entire state of the world, because there is an accident somewhere in New York, or because there are works on Sixth Avenue or what have you. And of course, there is the type of feedback that players receive. So, as you can tell, depending on how we choose to model each of these elements, we might end up with a completely different game theoretic model. So in this talk, I'm going to focus on the aspect of time. I'm going to focus on both continuous time and discrete time processes. Basically because the continuous time process will facilitate our understanding, or did facilitate in the past our understanding of what we can expect in a discrete time context. For the players, we will focus exclusively on continuous non-atomic populations of players, exactly like in Minfield games. So populations like flows of cars in New York. The actions, we are going to consider that these are finite in the population of players. And so you can take a certain path on the Manhattan grid, but you cannot take any possible path going through buildings, going through parks. So this is not a Minfield. We're not going to be talking about Minfield games per se, where you have a continuum of actions. This is what we would like to reach. This is the destination we'd like to reach in terms of analysis, but we're not there yet. So I want to make this clear from the outset. And finally, in terms of rewards, we're not going to consider stochasticity coming from nature or from some other godlike entity that might be perturbing the game for any reason. All right, we're just going to focus on endogenous reward mechanisms. So mainly we have a game. All right. So to recap, this is our basic framework. We have multiple agents with each with their individual objective. Their payoffs or their losses are determined by the actions of all agents concurrently. And then based on these payoffs, players will adjust their actions and the process will repeat over and over again. And what we want to see is whether this online decision-making process, this online learning process actually converges to some sort of stable, rational outcome, and under what conditions this can take place. All right, so that's the general intro. Now to delve into the model per se. By the way, do I have 50 minutes or I'm not sure, I don't remember.
Yeah, sure. I think like we have like roughly 1 hour in total. So from now,
Okay.
roughly 50 minutes.
Okay, great. Great. I just wanted to make sure. All right. So now, in terms of the model, in general, we're going to be talking about games in normal form, which in their most abstract way simply comprise a set of players, a set of actions per player, and an ensemble of payoff functions, one per player, defined on the Cartesian product of the player's actions. All right. So of course, in general, in game theory, there is a big distinction between whether we have an atomic or a non-atomic set of players. Likewise, for the action set, as we said, whether they are finite or continuous, whether they are shared or each player has their individual set of actions, etc., etc. I'm going to skip the definition of the non-atomic congestion games because this is not so important, and I want to focus directly on these two dichotomies that we have between continuous and finite player sets and continuous and finite action sets. All right, so depending on where we are, we could either be talking about finite games where everything is finite, population games where we have a finite shared action set and a continuous population of players. Finally, Minfield games where we have continuous player set and continuous actions, and continuous games where usually we have a finite number of players, but each has a continuous, typically compact strategy set. All right, so in terms of congestion games because, again, depending on how you model things, you may have completely different equilibrium structures, payoff structures, game structures. In the finite case, this is what we call the atomic non-splittable congestion games. When we have a finite number of players and continuous number of actions, we have atomic splittable. And finally, when we have a finite shared number of actions and a continuous population of players, we're talking about non-atomic congestion games, or which is a special case of population games. And all our talk will be here, and I will be trying to make little nudges to get from here to the fourth quadrant, which is the mean field games. And I will try to explain what are the difficulties that we face. And most of these difficulties will have to do with the fact that over a discrete set of actions, the set of probability distributions is very simple to handle. The moment we go to a continuous set of actions and we have to handle a continuous or possibly continuous, but also possibly singular distributions over this continuous set, then all hell breaks loose. I will try to explain these things as we go along. All right. Now, the specific type of game theoretic model that we'll be using, we'll be talking about both single population and multi-population games. In the single population games, which is simplest to describe, we have a population of players modeled by the interval from 0 to 1. And this is important. This is why we call it a population or an anonymous non-atomic game. We have a common set of actions. So it's not like every player has their individual set of actions. So we would have a continuum of different action sets per player. Okay, every player in 0, 1 has the same common shared set of actions. Now, a strategy profile in this setting is any measurable assignment of a player to an action. All right. So this captures the entire possibility of assigning, in a measurable way, of course, different agents to different actions. But usually what will be much more useful to us is the induced distribution or the induced population state, which measures the mass of the set of players that are using a specific action. All right, so this is the standard push forward of the Lebesgue measure under this strategy profile, this mixed strategy. And the anonymity condition that I alluded to is that the payoff to a player does not depend on the identity of the player. It only depends on the action that the player chose and the population state. All right, this is what I'm introducing here. The payoff function for type A, which is simply a function from the simplex of possible population states to R. All right. So I want to make this distinction because, again, in mean-field games, depending on whether we have first-order mean-field games or other models, these may or may not hold. And anyway, everything that I will show will depend very heavily on this anonymity assumption. If we're talking about a general non-atomic game in the sense of Schmeidler, where we have to keep track of the entire strategy profile, then again, all hell breaks loose. I will not show anything about this type of models. All right. So that's about the single population model. The multi-population model is basically similar. It's just we have also different populations, and we are allowed to draw from this finite set of populations. I don't want to go into too much detail. What I would like to explain a bit more is a specific scenario which is called symmetric random matching, and which connects population games with ordinary finite games like rock, paper, scissors, or matching pennies, and all that. And in the single population case, this random matching scenario is simply the following, works as follows. We have this population of players. If we are playing a two-player, in the symmetric case, we have a two-player symmetric game, like rock, paper, scissors. We are drawing, based on the distribution, on the state of the population, we are drawing two players, 1 and 2, based on the same distribution, and we pair them together. So in that case, the mean payoff to an alpha strategist will be simply this the multiplication of the population state with the payoff matrix of the game, and we will be looking at the alpha component of the corresponding vector. The reason I'm mentioning this is that in the multi-population case, this is a bit there is a bit of a difference. Why? Because in the asymmetric, in the multi-population case, because we are drawing players from different populations, possibly with different states, the payoff functions of AI type players that belong to population I do not depend on the state of the population Xi. All right, this is the only difference that that we need to keep in mind. Basically, that they are linear in all other population states, but they do not depend on the current population state. All right, that is the big difference, and it is worth keeping in mind because these models look very similar, symmetric and asymmetric random matching, but they end up having drastically different properties, and we'll come back to it later. All right, so one in terms of preliminaries, just to finish up, what we're going to consider as a notion of equilibrium, that will be the notion of a Nash equilibrium properly ported to this non-atomic context. The principle is that no player has an incentive to deviate from the chosen strategy if other players don't. And I should actually write here, well, almost no player in our context. Why? Because we're talking about non-atomic games. The choices of a set of players with no mass does not impact anything. So we could relax this definition if we wanted to. Anyway, mathematically, what is important is that we have this very nice characterization of Nash equilibria, which tells us that whenever a type is present in an equilibrium state, then the payoff corresponding to this type is no lower than the payoff of any other type, whether the other type is present in the equilibrium state or not. And there is a further reformulation of this principle as what is known as a variational inequality, which tells us that a profile X star is a Nash equilibrium of a population game if and only if it satisfies this variational inequality, as this is called, this inequality, which is simply well, in a certain sense, it is a first-order stationarity condition. Geometrically, what does this mean? It means that if we look at the simplex of population states of the game, okay, this could be a product of simplexes in the multi-population case, it doesn't matter, then the payoff vector at an equilibrium must be normal to the simplex. So here, the plane of the simplex is the plane of the page, like that. So here, the payoff vector at equilibrium is directly perpendicular to your screen. Now, if I move this, this is the case of a fully mixed equilibrium, which means that we're at the interior of the state space of the game. If we move this equilibrium to the side of the simplex, then these outward pointing, we could have outward pointing vectors that are simply, that simply belong to the so-called normal cone to the simplex at said point. All right, this is a mixed Nash equilibrium, but not a fully mixed Nash equilibrium because it is not in the interior. And we could even move it to a corner, in which case we have a pure Nash equilibrium. Now, in the pure case, the normal cone, which is the set of vectors that form a negative inner product with every displacement vector in the simplex. Here, it could so happen that this outward pointing vector, that this equilibrium payoff vector, could actually lie in the interior of the normal cone. When this happens, we say that the equilibrium is strict. And why do we say this? Because then these inequalities are strict for all profiles that are different from the equilibrium. Now, why am I mentioning this? Because this tells us something very important. If I perturb the game somewhat, then this arrow might be somewhat perturbed, but it will still remain within the interior of the normal cone. So strict equilibria like that are particularly robust. And so, in a sense, solutions of this variational inequality that are strict will end up being particularly stable in a sense that I will define later. But yeah, this was just meant to give you an idea of the type of the games that we're going to consider, the type and the possible structural differences between the different types of Nash equilibria in this class of games. All right, and just to finish up, I want to say I will focus on two specific classes of games. The first is a so-called class of potential games. These are games where the payoff field, this conglomerate, this aggregation, this ensemble of payoff vectors, one per type, can actually be expressed as the gradient of a potential function. This is one class. The other class is what the class of games known as monotone games, and monotone games satisfy these weird-looking inequality. I mean, if you have seen it before, then it is not weird. If you haven't seen it before, you say, what's going on here? It is less mysterious than it appears. Without going into the details, I will simply say that this is the game theoretic equivalent of a convex function, or rather a concave function, since we're minimizing. What this means is that if we define the Hessian of the game to be a huge matrix with blocks of the form del xi del xj of ui, all right, so we define this huge matrix, then what this monotonistic condition asks is that this matrix be negative definite, just as the Hessian of a function is negative definite if and only if the function is concave. All right, so potential games are those games where their payoff field is actually a gradient field, so they should be thought of as very close to functions in a sense. And monotone games are those game theoretic analogs of what concavity or convexity, depending on your point of view, is for an ordinary function. All right, what is particularly pleasant is that the class of non-atomic congestion games, which was the starting point of all our analysis, is actually in the intersection of these two classes, because it admits a potential, and this potential is a concave function, which in turn means that the game is monotone. All right. So these are, when I present, the results that I'm going to present are going to be primarily for these two classes of games, and I will discuss certain specific results for equilibria with particular structure, like pure or strict along the way. All right. Okay.
Sorry, can I ask a quick question?
Yes, please. It's perfect,
Okay.
Spawn. It's a perfect point.
Okay, thanks. So I had a naive question, but I'm sure you explained it, but I forgot. Where do we see the non-atomic component? Was it so when you introduced the game a few slides ago?
Yes,
Was it this
exactly.
measure? I mean, is it
Yes.
necessarily the Lebesgue measure on the 0-1 interval, or could you take any
All
measure?
right. All right. So here, so just to because there's actually this is a very good question. So let me just take a few seconds to unpack it. First of all, in reverse chronological order, this measure, yes, it is supposed to be a Lebesgue measure. It could be actually any non-singular measure if you prefer. But if we're talking about singular measures or at measures with atoms, then by definition, we are no longer in the atomic setting. All right.
Okay.
So so if we take a measure with atoms, this would mean that the definition here that these notions of equilibrium would need to be somehow changed. Now, um, to reply to your second question, which is where did the non-atomicity go? Suddenly we started talking about vector fields. This was actually intended. I wanted this vector field, which is formed by, which describes basically the payoff to a type of players given the population state of the game. This vector field completely characterizes, completely captures the strategic aspect of the game, because all the game's equilibria are defined based on this vector field, and all the analysis is going to be done, or rather all the learning is going to be done based on precisely this vector field. So if I forget the game theoretic structure, the non-atomic structure, and I focus on the vector field, then this essentially captures everything we need to know about the game. All right.
Okay.
Okay. Sorry, I have a problem. All right. Sorry about that. Okay. Any more questions?
I think there was one question from the audience. Anas.
Oh yeah.
Do you want to ask a question? If you want, you can unmute yourself and ask the question, or you can type it if you want. Anas, we cannot hear you, I think.
I can't hear.
Sorry, I think we cannot hear. If you want, you can type it, or
yes, maybe you can type, and then I can circle back to it as we go along when it's ready.
Yeah, maybe. Yeah, how about we continue, and maybe Anas, you can type your question in the meantime, and then we
yes
get back to it later. Okay, thanks.
All right, perfect. Okay. All right, so on to the type of learning processes that we will consider. Now, again, there is a very important technical subtlety, which is often glossed over, but it is quite significant mathematically. So usually, what do we mean by learning in a population game, at least for the purposes of this talk? It means that players will choose a strategy and they will receive some payoff. And depending on the outcome and some information revealed, they will choose their strategies and they will play again, and this will happen over and over. So mathematically, we will be assuming the following type of process: that the population at time n, the population is at state xn, and then the players will observe some common information variable, some common state variable zn. This could be, for instance, the sum of their payoff, their distribution, something. We will see different instantiations of what this looks like in the sequel. And then there is some function, some mapping, which defines the dynamics of the learning process, that defines the new state of the population as a function of this state variable Zn. And this state variable could also include in its definition the current state, the current population state. So this is a very general framework. Now, where's the catch? We are very used to saying that we have these players, which is a continuum of players, and then every, based on some distribution, they pick an action, and somehow, because there are so many of them, there is a law of large numbers that kicks in, and in the end, their choices are distributed exactly according to the original distribution, so to speak. All right, this is the standard assumption that you can see in especially in economics. It's something that you always see. The problem is that this type of framework, is actually meaningless. Meaningless. Why? Because when we're talking about a continuum of IID random variables, it is not possible to have a law of large numbers. So in particular, what I mean by this is that if each agent from a continuum of players independently draws an action according to some distribution, then the distribution of the realized draw may not equal P. All right, the distribution with respect to which we are drawing actions. This is highly non-intuitive. This was a result originally due to Judd in the 80s, and it was actually very bad news for a lot of the econ literature, which starts with a continuum of agents that are picking things in an IID fashion, and then we're assuming that some law of large number kicks in. And this is what I want to say, that we would like to be able to say that this is the learning model that we choose in our population game or in our mean field game. Regrettably, we cannot say this, precisely because of this non-measurability result of Judd. So here, even though this is the process that I would like to model, when I'm writing this, there is a certain gap between this endogenous model of continuous IID choices and what we end up choosing. To my knowledge, this gap cannot be resolved, but if any of you happens to know something about this or has encountered it in one form or another, I would be super happy to talk about it more. Now, let me just see the question.
Right. Yes, I think there is one question about the separation between atomic and non-atomic games, and whether we could use some mix, maybe measures that mix continuous.
All right. Yes. All right. So this is essentially quite close to your question, Mathieu. And yes, when things start mixing, this where is it? Let me find it. Yes, this characterization of equilibria that I presented is not necessarily meaningful, and this here this this condition is not necessarily meaningful either, because if we have a mix of atomic and non-atomic players, then we have to treat the non-atomic players differently, because they don't they are transparent relative to transfers from one strategy to the next, and we have to treat them differently to atomic players that, of course, have a significant impact both on each other and the entire population. So there is a very nice paper for mixed player roles, which is by Sylvain Saurin and Cheng Wan. I think it was 2016. Now I don't remember the title of the paper, but I believe you should be able to find it just by the authors and the year. And if you can't, then I'll be happy to send it to you later. All right, is this more or less clear why it is? Okay, great, thanks. All right, so now, as I said, this is a modeling problem which we are not going to even try to tackle. And
I think there is
yes?
one more question. Sorry for the interruption.
Yes, please.
Zedad, do you have a question?
Yeah, sorry for interruption. So my question here is that in this framework, you said the state xn is an individual state, right?
The state xn is the state of the population, the distribution of the population at time n. Yes.
Yeah. So, but the state variable, and by the definition of state variable, is the state is a population distribution, right? Z.
Mm-hmm.
And in this dynamics definition, the agent net states is only related to the state distribution. Is this framework for the atomic or non-atomic?
Everything I'm saying, all the frameworks that I'm presenting are for non-atomic games. All right, and here, this common state variable Zn, just to be clear, as I said, this could include xn and a bunch of other things. All right, so
yeah. So, but the definition of Z is just the average or distribution of the states.
For now, these are just examples. I will instantiate what Zn looks like when I'm considering different algorithms. Okay.
Okay.
So for now, this is just an abstract thing which can capture anything. But I'm going to instantiate both this and f. All right.
I see. Yeah. Thank you.
Okay. Yeah. Any other questions? I think
we're good for now. Thanks.
Okay. All right, great. All right, so I'm gonna start with a very classical process, which is known as fictitious play, and which dates way back to the 50s. All right, and what does it look like? It tells you that the state of the population at time n+1 is a best response to the empirical frequency of play up to said state. All right, so this xn bar is just the empirical frequency of the empirical frequencies of the population up to stage n inclusive. All right, this is our observable. This is the common state variable that we will be basing our decision on, and the rule that we are going to use in order to update the population state is simply a best response. All right, so we're taking the argmax of our of the population mean payoff. All right, this is what this inner product represents. All right, this is fictitious play, standard, as I said, Brown and Robinson in 51. Now, there is a variant of this process, which is called regularized or smooth or perturbed fictitious play. And the difference is that instead of playing a best response, players are playing, the population is playing an epsilon approximate best response to the empirical frequency of play. All right, this H function here is a regularization function for which I assume that it is only continuous and strongly convex. All right. For those of you that are familiar with mirror descent, this would be the distance generating function, which also goes into dual averaging, mirror approximation, all these algorithms. All right. But other than that, we have the same observable. So we are basically playing, well, not a best response to the empirical frequency of play, but a perturbed best response with the perturbation weight epsilon here, measuring the weight of the regularization. All right, this is our perturbed best reply, which goes in here. And this is this choice map, which will be useful in the sequel, basically eliminates the middleman here. Instead of saying we're playing a best response to a strategy, this Q map, this quantal response map is playing is a corresponding best response to a payoff vector. All right, so the two of them are basically the same thing. All right, this is regularized fictitious play. There is another variant of this where the weight of the regularization goes to 0 over time. So we may start with a lot of regularization to incentivize exploration, and then over time we are converging to fictitious play. All right, we are emulating rather fictitious play more and more. And then there is a different approach, which instead of looking at the average, is looking at the aggregate. And this in the online learning community is the policy known as follow the regularized leader, or FTRL. In the optimization community, it is known as dual averaging, and it is very closely related to descent. And the way it works is that instead of best responding or approximately best responding to the empirical frequency of play, what we do is we look at the aggregate payoff collected by each strategy over time. We modulate that by some learning rate parameter. All right, and then we are playing essentially a best response to this vector. All right, so here the observable is no longer the empirical frequency of play. The common state variable that we are basing our reaction on is this score type variable, this propensity, which measures how well a strategy has been performing over time. Because here, if a component of this vector is very big, this means that over time, that strategy will have accrued a lot of good payoff, which means that probably it's a good strategy to play. All right. So this is why I will sometimes call these as score vectors or propensity vectors. All right. And what I'm saying here that this is the empirical frequency of play. This is a typo. I'm sorry. This is just this propensity variable. All right. Yeah. So let me just link these dynamics together. It is the clearest way to see the link between them is in the case of random matching scenario, where we have this linear payoff structure. So we have a finite game with a certain symmetric payoff matrix M, and so this vector of payoff function is simply M times X. And because of this linear structure, we have this transparency to averages, which means that when we are looking at the payoff vector associated to the empirical frequency of play, this is the same as the empirical frequency of the payoff vectors encountered up to said time. All right. So M, the payoff, can go in and out of the averaging process. And because of this, in random matching games, we can encapsulate all these dynamics with the same FTRL type formulation. All right. What I wrote here is simply the recursion associated to this to the FTRL dynamics. I just opened it up and developed it. I didn't do anything interesting. But what is interesting to see is that the FTRL dynamics can be seen as a vanishingly regularized fictitious play if the learning rate is chosen in this way, where epsilon n is the weight of the regularization, and note that there is still this n here, or as a regularized fictitious play if the epsilon weight is constant. Note here that the effective learning rate in that case would still be variable because of this lack of 1/n factor, and this because here we are aggregating, we're not averaging, even though the name of the algorithm is dual averaging. We're actually aggregating things here. We're only averaging if this eta n is 1/n, but this is not the case, as we shall see. And finally, the fictitious play, the original fictitious play, is recovered either when we formally set this n times eta n equal to infinity, or whenever we take no regularization at all. All right, the regularization choice h is equal to 0 is not formally allowed because we want our h to be a minima, strictly convex, if not strongly convex. So, but this is why I put this in quotes. All right. So, these are the algorithms, in a sense. These are the discrete time processes. We can also look at the continuous time limit of these processes, which is something that takes place when we simply rewrite, for instance, fictitious play in terms of the empirical frequencies of play. In that case, we can see that the whole process looks like a discretization of an ODE with a step size of the form 1/n, 1/n plus 1 in this case. All right. But then this also suggests that we can see all these processes as discretizations of suitable continuous time dynamics, of continuous time ordinary differential equations. In the case of fictitious play, the corresponding dynamics are the best reply dynamics by Gilbo and Matsui in 1991. In the regularized fictitious play case, we get the regularized best reply dynamics, which were also studied by Hofbauer and Sandholm. The vanishing case, here this reference is wrong. This should read Benaim and Faure. Let me write this. This is Benaim and Faure in 2013, I think. And the dynamics of FTRL, which were originally derived by Charles Schwartz in the discrete time case, they have also their continuous time analog. All right. The reason that I want to mention this is twofold. First, because the analysis is going to be much easier in the continuous time cases, so this will be a springboard for the discrete time case. And secondly, because especially in that case, we recover some very well-known dynamics from game theory, and in particular, if we take the choice map to be, if we take the regularization function to be the entropy, it turns out that the corresponding Q map, the corresponding quantum response map, or the corresponding perturbed best response map is simply the logit choice map, which assigns probability, or which assigns mass exponentially proportional to the propensity of playing a certain strategy. All right. So in that case, the FTRL dynamics are equivalent, boiled down basically, to the standard replicator dynamics, which you may have seen in the study of population games. All right. So very quickly, what do they, especially in the case of the replicator dynamics, what do they actually look like? Here, if we take a congestion game, you see that the profile is particularly amenable to learning, because all trajectories converge to some strict equilibrium, except a measure 0 set which converge to to an otherwise unstable interior equilibrium. If we take the battle of the sexes situation similar, however, if we take a zero-sum game, then we have this cycling behavior. All right, things change there. And the moment we move up from 2x2 games to more complicated games, well, things can start mixing up quite a bit. Of course, we can still have nice convergence profiles like that, where strict equilibria attract everything. But we could have a mix of different locally attracting equilibria and some sort of recurrent behavior in some other part of the game, or a completely recurrent behavior, or other types of behaviors like weird attractors coming in, etc., etc. So all this just to say that after a while it becomes a jumble, even in this very simple case. So we have to specialize our analysis. And we will specialize our analysis in order to get global results in the class of potential and monotone games. And the first result that I want to show is that if we have a potential or a monotone game, then every solution orbit of the best reply dynamics, which is a continuous analog of the fictitious play process, converges to an equilibrium, to the equilibrium set of the game. All right. This result was originally due to Hofbauer and Sandholm in 2002 and 2009, respectively, for potential and monotone games. And what you can almost immediately deduce from this is the following theorem for fictitious play, the discrete time process, which tells you that if you have either a potential or a monotone game, then the empirical frequency of play under fictitious play converges to the set of equilibria. Modulo a very technical condition here, which is almost always satisfied. This is really mild, but this is something that we need in order to apply a very powerful theory known as stochastic approximation for differential inclusions. We're talking here about inclusions, but because in general we have best replies, which is a set-valued map. All right, so this is why we're talking about this. And anyway, this is a technical condition which we need in order to invoke this general theory. This general theory, however, once invoked, is extremely powerful because it tells us that basically the continuous time dynamics and the discrete time dynamics share the same set of limit sets. I'm oversimplifying, but this is basically what they're saying. By the way, I see here a question on the chat. Is it okay? Yeah, is it okay if I plead the fifth for like a few more minutes just to present the results and then circle back to you?
Yeah, sure. Maybe we can do like that, if it's okay with you, Jan.
Yeah, okay, great, thank you. All right. Now, this is for fictitious play. If we go to regularized fictitious play, then morally we have the same type of result. It's just that instead of talking about the actual game, you will see here that I'm talking about a modified game G epsilon, where epsilon is the regularization weight. Other than that, the theorem is exactly the same. Solution orbits of regularized best reply dynamics converge to the equilibrium set of this perturbed game. And likewise, the empirical frequency of play of regularized fictitious play converges to the equilibrium set of this perturbed game. What is this perturbed game? It is the original minus epsilon times the regularization weight times the gradient of the regularization function. All right. So the equilibria of this game are, in a sense, epsilon close to the equilibria of the original one. All right. Now, this is good news because it suggests that if we take epsilon to 0 over time, as we do in vanishingly regularized fictitious play, then we should be able to recover the equilibrium set of the original game. And indeed, this is true modulo an additional technical assumption for h in continuous time. But in discrete time, I don't know. we don't have a result. I believe the result is true, but what also happens is that we can no longer use the theory of stochastic approximation that we used to prove our previous results. All right, and this because we no longer have an autonomous system. Here we have time explicitly as part of the dynamics, and this makes the stochastic approximation theory non-applicable. All right, and the thing is that even the continuous time proof is significantly more difficult than the standard best reply or regularized best reply dynamics. So it's not like we can directly harvest it from the continuous time proof either. All right. That's for regularized best reply dynamics and vanishing regularization. Finally, let me close up with FTRL. The easiest case is when we have a constant learning rate. All right. And in that case, what you can show is that if you have a potential or a monotone game plus some technical assumptions for H, which I will discuss, then every solution orbit of FTRL converges to equilibrium. And importantly, I'm now talking about the actual solution orbits. I'm not talking about time averages or the empirical frequency of play. I'm talking about the actual day-to-day trajectory of play of the population. All right, this is for a constant learning rate. If we have a non-constant learning rate, then we need to have a control over how it goes to zero. It cannot go to zero too fast. It can only go as fast as omega of 1 over t. All right, but as long as this is satisfied and we have the same set of technical assumptions, then every solution orbit converges. Well, here I'm mentioning something as a globally evolutionarily stable state. This is a very important notion in the the context of population games, which was introduced back in the 70s by Maynard Smith and Price, and basically is the solution of this dualized version of the variational inequality that I showed in the beginning. This is called the Minty variational inequality. And it tells you that if you have a state, an evolutionarily stable state, which solves this inequality, I don't want to get into the biological motivation for this condition, but if you have such a state, then the dynamics of FTRL converge to it from any initial condition as long as this growth rate, decay rate rather, for eta is satisfied. All right, this allows us, I mean, all strictly monotone games admit a GSS, but we don't have the result for potential games, and in the context of a non-constant learning rate, it is a bit elusive. So that's the continuous time case. So let me finish up with the discrete time case, where you can have a result about again evolutionary stable states. The way that the learning rate must grow is a bit different here, but the result is otherwise the same. The sequence of states converges to a globally evolutionarily stable state from every initial condition. This gives you convergence whenever you have a strictly monotone. Why is it not changing? Okay, sorry. For some reason, what happened? Let me stop sharing for a moment because I cannot change my slide for some reason. Sorry about that. What happened? Great. Okay, let me be very quick about it. Let me share directly my computer, a window. I can no longer share my screen. Is there a feature with the Google Meet that deactivates after 1 hour?
I don't think so.
Okay.
Let me see. Okay, I don't see any feature that would prevent screen sharing, but
because when I click on presenting, you know, I will just and I cannot even share my entire screen for some reason.
oh, I see. On my side, it looks like I could share screen, so
I can
do you
send you
want
the
to try
slides.
to leave and join again, or you can? Yeah, you can
Well,
just...
let me actually, you know what? Let me wing this. Let me hand wave this, and because I was already at the end of my talk anyway. The only thing I wanted to add is that in the case of when we have a global evolutionarily stable strategy and we have the discrete time FTRL, we have this global convergence result as long as this condition for the learning rate condition is satisfied. What my last slide was going to show was the extensions and the steps that we are trying to follow to get final to mean field games. So let me wrap this up with a sentence that, of course, I'm sweeping a lot of technical details under the carpet, but the result that I presented can basically be extended to the case where we have a finite number of players and compact action spaces, or finite number of players, compact action spaces, and we are playing mixed strategies, so probability distributions over these compact action spaces. All right. So far, this is something that we can get. The last part of the approximation, which is going from a finite to a continuous number of players, which is what we want to at least capture first-order mean field games, this has so far proven elusive. There are some partial results on this by Saeed Hadikanlu, which was one of the co-authors of the paper that I presented. Yeah, I'll stop here and we'll be very happy to take questions and retry to share my screen.
Okay, thanks a lot for the very nice presentation. Sorry for the glitch with presenting. We can try again. If you want to share, if you want to send me your slides and I can share screen.
Yeah, I can do that.
Okay. And in the meantime, if there are questions, so I think there was at least one question in the
yes,
chat.
by Ian. By the way, I sent you the slides, so
okay,
yeah.
Thanks.
All right. So, double Oracle PCRO, I'm reading the question that a Nash distribution over empirical play is used rather than a uniform weighting in FTRL and fictitious play. Has a link between a Nash weighting and that implied by the choice of step size been explored? All right. So, just two things here. There is an important distinction between a learning rate and the step size. I want to address this because you could either take your, it is different whether the payoff vectors enter FTRL, enter your algorithm with the same weight, and then you are multiplying the sum, all right, which is what we did in this presentation. This is a learning rate, or if they are entering the algorithm with possibly different weights, and this different weight is basically the step size. So in your question, are you making this distinction with the step size and the learning rate, or do you mean just learning rate? Because my answer will have to be different.
So I meant the way that you're, so like at the beginning of the presentation, you talked about taking a historical average.
Okay,
over
great.
Strategies or payoff vectors or whatever. Yeah.
Perfect. I just wanted to make sure that I wasn't missing anything. So yeah, in that case, yes, the link between this, the link between all these is the slide I showed when I was making the link between the dynamics where a choice of eta n, the learning rate of FTRL, is equal to 1 over n epsilon, epsilon being the regularization weight, which defines basically the Nash distribution and the difference between the Nash distribution and Nash equilibrium. This is the best link that I can think of. All right.
Okay.
Does this answer your question though?
Yeah, well, I guess you're saying that's where you should look, but I'm asking, has anybody, you can run this algorithm and then you can look to see, does that weighting actually look like the Nash distribution over historical checkpoints if I was to compute it?
That I don't know.
Okay.
That
I just know that this is something people do in finite games that that maybe they're not doing here. I've never seen anybody explore these two things.
Yeah. Yeah, I'm not sure about that. Yeah.
Okay, thank you.
Yep.
Okay, thanks. Sorry, I think I haven't received the slides yet for some reason, so I'm sorry I cannot share. But if there are other questions or
maybe
it's
let me
just
check my send.
My mailbox maybe.
Yeah, Mathieu Laurier at NYU EDU, but
yes,
maybe it's because they're 5 megabytes and they take some time. I don't know.
Maybe I will receive them in a moment. Yes, one more question, Anas. Okay, I think unfortunately we cannot hear you. Apparently, you are unmuted, but I think there is some sound, some issue with the sound, maybe. Sorry, we cannot hear you. Maybe you can type your question and. Okay. So about the mean-field games, what you were saying at the end, is it because I think there are some, it's possible to consider mean-field games with finite action spaces in some cases, but maybe you have in mind the continuous action spaces. Okay, and this is the main source of difficulty in your case, having a continuum of players and a continuum of actions.
Yeah. Having one of the continuum, having one of them being continuous, we can handle. We can even handle if it is infinite. If the continuity is infinite dimensional on the side of actions, but both of them at the same time, it is difficult. Again, the only works that I know are by Said and his advisor at the time, Pierre Cardagaguet. 2 papers that they wrote together. But these are for fictitious play and for smooth fictitious play, if I'm not mistaken. But it's technically frustrating, to say the least.
Okay, I see. And about the continuum of IID random variables, I think so. With Alexander Orel, who was here, and yes, great. I think now it works.
Let's see. I tried again. Can you see my screen now?
Yes, we can see your screen.
Okay. Well, it's not perfect like that, but at least I can point to something. Yes, please tell me.
Yeah. So about the continuum of IID random variables, I think there are some extensions using the exact law of large numbers and some abstract Fubini extensions, etc. So I think economists like Sun and Duffy have tried to come up with ways to have continuum of random variables.
There is an extension theorem, actually an extension theory, I should say, which is like a Kolmogorov extension theorem. It is Ionesco-Talsi, I think, the mathematical theory, which basically allows you to extend the measures and recover certain results. Now, I want to be perfectly honest. This becomes so technical so quickly that maybe you can actually say things. I don't know if the results that you mentioned are along the same lines. I don't know. It's personally, whenever I go into this question, I try to ask another question because it gets too technical too fast.
Yes, and maybe in this type of games, it's not really required because people interact only through the aggregate. So I'm not sure if you ever need. Yeah, I mean, I don't know. I think the way you formulate it, maybe you can kind of avoid this issue. So
Yes, this is, I wanted to be mathematically correct, so this is why I said, this is my model, this is the motivation for my model, but I cannot make the precisely, the exactly formally correct, formally precise. Yeah.
Okay, thanks. Thanos, you have a question?
Yes. Thank you for the very nice presentation. I have two questions, basically. They are kind of not very restricted to your presentation. Where do you fit the correlated equilibria in the setup? Like,
I don't.
You don't need to consider them. You don't need to consider them because the assumptions just give you strict.
I do not, and let me explain why. Because here, I mean, correlated equilibrium is something where, at least the type of correlated equilibria that we are accustomed to, have to do with finite games, right? The moment you try to define correlated equilibrium for anything, for any other type of game, then things can become real dicey real soon. Here, in general, yes, finite games are a special case of population games, but the results I presented are for general population games. All right. So, and in a general population game, the notion of a correlated equilibrium is not necessarily meaningful.
Why do you say that? Can you give more? Why do you say it's not meaningful? Can you give a little bit more?
Okay. Well, first of all, one first question is how would you define it?
Just to see if I understand correctly. Like, you would mean that if I have a mediator that is going to randomize or to give this to like condition the things that gives the suggestion, and then the other gives the signal, and the other players play condition on the signal, then you would say that maybe because of the non-atomic nature that there is no meaning to that.
I would say, first of all, that in the very definition of a correlated in the very definition of a correlated equilibrium, you need to have very properly assigned payoffs to, you know, pure strategy profiles, which is not the case in a general population games. The setup, the definition is completely different. Yes, if we are looking at population games that are coming from random matching in a finite game, then yeah, of course, it could make a certain degree of sense. But if you're looking at a general non-atomic congestion game, for instance, what would a correlated equilibrium be that in the case? What would even the space of correlated strategies be in that case? All right, it is fundamentally different.
Okay, thank you for.
Yeah, I'm not trying to evade the question. I'm just saying that once you get out of the, I mean, especially as game theorists, we have sort of this Pavlovian reflex to think about finite games. But once you get out of the realm of finite games, a lot of things that are second nature for us in the context of finite games stop. You can't even really define them.
My second question is kind of related to the first one. Like, could you consider stochasticity, or you could consider stochastic dynamics like this F to also include some noise, or to
for sure. So here a very easy way of introducing stochasticity would be to say that you are not necessarily best responding to you don't have accurate observations of your payoffs here, or it would be even clearer if I went into to FTRL. So you don't have accurate measurements or representations of your payoff vectors. Instead, what you have are noisy versions thereof. All right, you could write it out here, and you would be getting a stochastic algorithm. All right, and then you could ask the very same questions that we did. I would say that in the algorithms where you have sort of a stochastic approximation machinery helping you, this is not too much of an issue. Here, the problem, if this eta n was actually inside the sum, it would be easier to handle. The way it is not super easy to handle. It is we definitely don't have any results in the paper for the framework that you are suggesting. I do believe it is interesting and things can be obtained, but I'm not sure to what extent this would pose a technical difficulty to get to a stochastic version or an almost sure version of the results that I presented. But this is a very, very good question and a very concrete research thread, in my opinion.
And to combine maybe the two questions in a final remark, if we have like, okay, my interpretation is completely like analytical and coming from stochastic control and stuff like that. I have not put my hands into this level of game theory. But if you consider like F as the flows that we usually have, like you consider that stochastic, then you wouldn't give some notion of correlated equilibria, because at least in the midfield game setup that we have seen, like if you have the correlated equilibria, you have the stochastic flows. So in some sense, if here you put like the stochastic flows, you wouldn't arrive in a correlated equilibria. Like maybe it is a chicken egg question, but I don't know. Also, maybe my interpretation for like the stochastic flows,
I don't know.
is not relevant. So
I don't know. I don't know. Sorry.
Okay, thank you. No, it was just curiosity. Like, I did my disclaimer in the beginning.
No. I just it's a very nice question, but I cannot give an informative answer. Sorry. Yeah.
No, it's okay. Thanks a lot. There is another maybe last question if you still have time, but
yes, of course. Oh yeah, I see in the chat.
In the chat.
Yeah.
So wondering in terms of convergence rates. So I think you mentioned something about convergence rates in continuous time and maybe in discrete time for FTRL.
Yeah. All right. Right. Okay. So let me go to the results here. No, let's. Okay, so just to be clear, in the actual paper, we forget the actual paper. There is a big difference when we're talking about rates of convergence for the time average of the process, for the empirical frequency of play, versus the convergence of the actual trajectory of play. All right. With respect to the former, the empirical frequency of play, if we use a constant learning rate in continuous time, we can guarantee you can guarantee constant regret and thus a 1/t rate of convergence to equilibrium in terms of time averages, of course, for monotone games. For potential games, when the potential is non-concave, the only thing you can say is that within time 1/t, you will you will be converging to criticality at a rate of 1/t, which is not the same as saying that you will be converging to an equilibrium. In discrete time, in the class of monotone games, if you use if this eta n, if your eta n here is taken to be 1/square root of n, which is allowed because this limit does go to 0 in that case. Then the rate of convergence of the time average is of the empirical frequency of play is rather 1 over square root of t. This cannot be improved by tuning the learning rate. At least you would need to consider a different process. And in terms of the convergence of the actual sequence of play, in this context, I have nothing for you. I don't know. Nothing is known as far as I'm aware. I don't know if you had a more, if you wanted me to zoom in a particular, in a special case.
We cannot hear you, I think. Sorry, Anas. Okay. I guess this is already very informative. Yeah. Yeah, thanks a lot for the answer. All right. I think it's already pretty late for you. Thanks a lot for taking time to answer all the questions. If there are no further questions, thanks again for the very nice talk. Very clear presentation.
Thank you for inviting me.